Take a look at our Module 7 lecture here related to asphalt pavement and materials. The topics to be covered in this module lecture are going to look at asphalt paving materials, super pave asphalt binders, asphalt concrete aggregates, and asphalt concrete mix design. One of the first things we're going to take a look at is asphalt or the bituminous materials we're going to use. And we're going to combine these with aggregates to make a pavement surface. Multiple layers for highways, thin dust control layers for the rural roads that we might be working on. And bituminous materials are defined as hydrocarbons that are soluble in carbon disulfate, usually hard at normal temperatures, softens when it's heated. Bitumens used in paving. Native asphalts are obtained from asphalt lakes, rock asphalts, or rock deposits containing bituminous materials, and tars are distilled or distillation of coal. Petroleum asphalts are the distillation of crude oil. Asphalt cements are made up of three types of hydrocarbons that fall under asphaltenes, resins, and oils. Asphaltenes are large, hard, powdery, black materials that are covered with the resins that contributes to its ductility and adhesiveness to the asphalt layer. The particles are suspended in an oily material that allows the asphalt materials to flow. The consistency or hardness of the asphalt cement material depends on the relative proportions of these materials within the mix composition. Aging and hardening of the asphalt material is due to the evaporation and oxidation of the lighter oily constituents during the mixing process at high temperatures, and to the oxidation of the oils to resins and resins to asphaltenes when used over a period of years. Design of the asphalt mixture must take into account these possible effects on the usefulness of life or the life of the pavement surface over time, and of course the environmental concerns that we're going to have for a specific area. Let's take a look at pavement viscosity. Grades and temperatures at which they are used depend on the viscosity of the material. Viscosity of asphalt varies with temperature, and it ranges from a solid to a thin liquid state. Viscosity decreases, or the material becomes more fluid as the temperature increases, which makes sense. It's hotter. The absolute dynamic viscosity is measured in pascals a second for the SI units and poses for the traditional units. One pose is equal to 0.1 pascals per second, or times seconds. Kinematic viscosity is measured in square centimeters, and strokes or centistrokes, or one stroke will equal 100 centistrokes, or it's going to equal 1 square centimeter per second. Kinematic viscosity equals absolute viscosity divided by the density, or 1 gram divided by a cubic centimeter for asphalts. The absolute viscosity and the kinematic viscosity have absolutely or approximately the same numerical value when expressed in poses and strokes. Viscosity has often been measured in the Seybold-Furl apparatus as the number of seconds it takes for a specific volume to flow. And you can see this in the PowerPoint presentation that accompanies this Module 7 lecture notes. Approximate conversion is 1 second, which equals 2 centistrokes, or equals 0.02 strokes. And of course, take a look at the figure and it'll show us the various types of viscosity measurements that are part of the PowerPoint presentation for this module. The following figures, again, you're going to see these in the PowerPoint presentations. It looks at temperature viscosity relationships of the asphalt cement. Of course, A10 or AC10 is harder than AC5. Reduced viscosity to the 1.15 square centimeters a second. Asphalt A must be heated to 167 degrees Celsius, and asphalt B only to 163 degrees Celsius. Temperature limits corresponding to the viscosities of 1.5 to 3 square centimeters a second are sometimes used. Again, you'll see this in the PowerPoint presentation, but asphalt A would require the plant to operate at temperatures between 153 to 167 degrees Celsius. The minimum temperature for spraying for pavement seal coats is often specified to a viscosity of 2 square centimeters a second, or 200 centistrokes. Of course, with this in mind, asphalt B would be heated to 156 degrees Celsius. Asphalt cements, primary asphalt products produced by distillation of crude oil. Various viscosity grades, with the most common being an AC 2.5, a 5, a 10, a 20, and an AC 40. Viscosity grades indicate the viscosity in hundreds of poses, plus or minus 20% measured at 60 degrees Celsius. Of course, an example of the AC 2.5 has a viscosity of 250 plus or minus 50, has a viscosity of 4,000 poses plus or minus 800. Liquid asphalts, also known as cutback asphalts, are mixed with a solvent to reduce the viscosity, commonly heated and then sprayed on aggregates. Solvent evaporates. Types of grade based on solvent used. RC rapid curing uses gasoline as the solvent. MC medium curing uses kerosene as the solvent. SC slow curing uses diesel fuel as the solvent, and they may be produced directly from the refinery during the distillation process. Solvents contents are usually between 15 to 40% of the total value. It is important to remember that grades of liquid asphalts are governed by the viscosity of the mix. Asphalt emulsions are mixtures of asphalt, cement, and water, are combined with an emulsifying, usually a soap agent. The emulsifying agent is used because the two ingredients don't mix well together in a normal mixing process. The emulsifying agent breaks up the asphalt cement and disperses it throughout the mix in the form of very fine droplets. The emulsion sets as the water evaporates. Emulsion contains approximately 55 to 75% asphalt and 3% emulsifying agent. Two general types of emulsified asphalts are produced based on the emulsifier that is used. These two types of emulsified asphalts are catatonic and anatonic. Catatonic emulsions have positive charged particles, while anatonic emulsions have negative charges. Anatonic emulsions adhere better to the aggregate particles with positive surface charges, like a limestone. Catatonic emulsions adhere better to aggregate particles with a negative surface charges, similar to a silicate or silica material. Catatonic emulsions also work better with wet aggregates and in cooler temperatures or weather. An emulsion's rate of hardening or breaking depends on the amount of type of the agent used. There are three grades of the two types of asphalts, with the letter C indicating that it is a catatonic or catatonic type. So rapid setting, RS or CRS, medium setting, MS or CMS, slow setting, SS or CSS. Let's take a look at the ductility test. And the ductility test of a bituminous material is the distance measured in centimeters to which the material will elongate before breaking apart when a briquette specimen of the material is pulled apart at a specified speed and temperature. Of course, this is in a controlled environment. And also, you will see this in the PowerPoint presentation. It'll go a little bit more into how the test is done and performed. But similar to the penetration test, we are looking to perform the test in a controlled environment, and unless otherwise specified, the test should be made at a temperature of 25 degrees plus or minus 0.5 degrees Celsius, and at a speed of 5 centimeters per minute plus or minus 5%. Viscosity grading system became the norm or standard in the 1970s for grading of pavement mixtures. This is due to the more accurate results that came from actually measuring the viscosity of the cement at higher temperatures. With this in mind, the grading system was more representative of the temperatures that were employed during the mix and use of the pavement properties during the overall installation process. As previously mentioned, standard viscosity grades are AC 2.5, 5, 10, 20, and AC 40. These values correspond to a penetration grades of 40 to 50, 60 to 70, 85 to 100, 120 to 150, and 200 to 300. The following tables, again, you're going to see these in the PowerPoint presentation, will give you the specifications for viscosity graded asphalt cements. Of course, the first table is going to be the ASTM D3381, the one that is normally used, while the second table is for the materials that have been graded or been aged in a thin film oven test. Superpave asphalt binders. The Strategic Highway Research Program developed these Superpave standards that are widely used in North America. Superpave comes from superior performing asphalt pavement. American standards have been developed for both asphalt binder and concrete mixes. It is important to remember that the cementing agent is termed an asphalt binder and not an asphalt cement due to the fact that modifiers are often required to ensure that the new requirements are met. Research indicated that pavements failed or cracked due to the following conditions. Permanent deformation or rutting occurring at high temperatures as the asphalt softens and the mix loses elasticity. Fatigue cracking due to high volume of load applications and aging of the asphalt. Low temperature cracking as asphalt becomes brittle and the pavement shrinks in cold weather. Superpave bases its specifications on high and low pavement temperatures expected at different geographic locations. And again, we've talked about this. We're going to have different conditions that are up in Maine, Montana, Minnesota, Arizona, Florida, and so on. High temp grades vary from 46 degrees to 82 degrees Celsius based on 6-degree increments. Low temperature grades range from -10 to -46 degrees Celsius. A performance grade of a PG 58-28 would be suitable for pavement designs for the maximum temperature of 53 degrees Celsius to a range of 58 degrees Celsius. The next lower temperature would be the PG 52 with a minimum temperatures down to -28 degrees Celsius. The Superpave program contains information or data from over 6,000 weather reporting stations in America and Canada. The collected information is used to assign a unique asphalt binder grades for the different locations that we have. Let's take a look at a typical grading based on the specifications. So we get the PG is the performance grade that we're looking at. The number 64 here is the average 7-day maximum pavement temperature. And of course, the 22 is the minimum pavement temperature. And we always have to want to remember that the grading system is based on the climate temperatures that are selected to perform the test. Modifiers are added to the asphalt cement to enhance resistance to rutting, low temperature and fatigue cracking, stripping and oxidation, and also in recycling operations. Rutting is a permanent deformation of the surface materials, and in order to meet the Superpave specifications when temperature grades are over 70 degrees Celsius and under -28 degrees Celsius, modifiers are necessary in order to maintain asphalt surfaces. Asphalt suppliers normally add the required materials in order to meet the specification performance grades indicated. Other types of modifiers or additives can be used with the asphalt cement or added directly to the mix within a plant setting. These modifiers or additives are used in order to improve durability, strength, or skid resistance to the final pavement surface. Modifiers or additives include polymers, natural latex rubber, cellulose, and man-made fibers. Recycled materials, of course we've seen this ground rubber, have been used in recent years on an experimental basis in order to determine their abilities to extend the life expectancy of the asphalt paving materials. As we know, over the years, these experimental considerations have not done well in the field with experimental tests based on going from a controlled environment to a environmental condition that maybe does not allow it to hold up as well as expected. Here's an indication of asphalt or pavement rutting. We can see the grooves in the pavement. We can also see some pavement fatigue cracking here and oxidation, the changing in the road. Asphalt concrete properties. The main asphalt paving material used today falls under the term asphalt concrete. Asphalt concrete is a high quality pavement surface composed of asphalt, cement, and aggregates that is hot mixed in an asphalt plant and then hot laid to form the road surface. In common terms, we call this blacktop. Hot mix asphalt are used on most roads and parking lots that are paved or surfaced. We also call it macadam and things like that. Rural and secondary roads are normally not paved and usually employ a lower quality pavement surfaces or alternative materials and R blend to create a supporting road surface. Asphalt paved roads must provide a stable, safe, and durable surface for the vehicular traffic to navigate through curves, incline differences, and so on. The properties of the asphalt concrete depends on the quality of the components used, the asphalt binders, the aggregate, along with the construction process employed, and the mixed design proportions specified, or the specifications. Aggregate concrete consists again of asphalt, cement, aggregates, and air. Due to the irregularity of the aggregate that is used, asphalt cement seeps into the voids and leaves these particles unable to coat and bind all the aggregate together. This leaves or also leaves more air voids in the mixture that would be expected when looking at and calculating the total aggregate to the asphalt volumes needed. The amount of asphalt absorption is less than the water absorption for the same aggregate and is usually about 50%. It is also or always important to include the volume of the absorbed asphalt within the calculations due to the fact that all the volumes must be measured accurately. The amount of asphalt absorption can be found by measuring the relative density of a mixture of the asphalt coated aggregates and comparing this with the value expected with no absorption. Stability and flexibility of the asphalt concrete. Stability of the asphalt concrete depends on the strength and flexibility of the mixture and the degree of compaction during the placing process. The strength must be sufficient to carry the load without shear occurring between the particles. Of course, the structure must remain intact. The main contributor to strength is friction between the grains. A dense grade or graded mixture composed of particles with rough faces with a relatively thin asphalt film between them is best for a high friction strength. Flexibility is also important as the pavement distributes the imposed load by deflecting slightly as the load is applied without cracking or, of course, permanent deformation. To meet all these requirements, a more open, graded mixture with a higher asphalt content is best. Strength and flexibility are evaluated by various tests depending on the design method being used. And of course, you can take a look at these different test procedures in the PowerPoint presentation for this module. Asphalt surface and the safety factor that goes with it. Safety is very important for the surface course of the road surface. This involves skid resistance and drainage of the water from the surface. Skid resistance is enhanced by using smaller size, very hard aggregates for the surface course. This provides more points of contact for the development of friction forces. Open graded surface courses are used in very heavy traffic areas to allow immediate drainage of the rainwater before it can result in hydroplaning. Of course, big concern with any road surface, we want to get that water off of it, so we eliminate hydroplaning. One of the reasons why roads are crowned in the middle so that it will run that water off to the sides. Hopefully we have a good drainage system that's going to allow that water to flow. These pavements also increase skid resistance due to the coarse texture provided, and open graded friction courses are not as durable as the usual pavement due to the potential for fairly rapid aging of the binding or binder materials. Durability of the asphalt concrete is critical to ensure that it maintains the stability and the skid resistant properties for the design surface life of the road surface. Asphalt ages and pavements become denser with time and traffic flow over the surfaces. Pavements fail due to the following conditions. We get changes in the aggregate, permanent deformation or rutting, cracking caused by fatigue or low temperatures, bleeding of asphalt to the surface. Let's take a look at what we can do in controlling some of these failure conditions. And in order to control these failure conditions, the following 7 requirements are usually specified or recommended. Our first one is we use a strong, sound, durable aggregates free of harmless amounts of deleterious substances. Breakage of particles during the transportation, placing, and service reduces the strength as there is no asphalt binding the broken pieces together. Traffic could polish the soft aggregate particles at the surface, reducing the skid resistance. Certain types of aggregate must be susceptible to stripping or placement of the asphalt film by water. Our second one is we use asphalt binders that are tested for resistance to fatigue cracking, rutting, and low temperature cracking for the geographic area of the use or the road surface climate conditions, as required under the new performance graded specifications. Our third is the maximum temperature during the mixing to help prevent premature hardening of the asphalt as the lighter constituents are driven off. We look at 4, the maximum percentage of the air voids to reduce permeability and movement of air and water in the mixture, and therefore, of course, reducing the rate of oxidation. 5, we look at the minimum percentages of air voids. This helps to ensure that asphalt does not bleed to the surface and reduces the skid resistance factors we may have. And a minimum amount of air allows asphalt movement without forcing it to the surface as the pavement deflects. We look at 6, the minimum percentage of the VMAs to ensure that sufficient space is left for the asphalt cement. This helps again to ensure that the binder film around each particle is thick enough to remain ductable. 7, the minimum and maximum percentages of the VFA. Asphalt content must not be too high for stability. The air void content must not be too high for traffic or light traffic areas or too low for heavy traffic areas. So in general, the controls on the VFA ensure that borderline mixes that meet other void criteria but may not perform well or are not used. Aggregates for asphalt concrete are usually classified as coarse aggregates, fine aggregates, and mineral fillers. Mineral fillers is often used in asphalt concrete mixes to supply the fines. Of course, we're looking at smaller than the number 200 size sieve. Fines are very important in producing a dense graded strong material. Many natural sands do not contain the amount of types of fines required. Limestone dust is most often or most common material used for the mineral filler that we're going to use. The aggregate materials should consist of the following. We get a well-graded, dense, including mineral filler, if required for the strength. We get hard for resistance to wear and to polishing due to traffic. We get sound for resistance to breakdown due to freezing and thawing. Rough surface. Crushed rough surfaces give higher friction strength and a better surface for adhesion of the asphalt cement. Cubical, thin, elongated aggregate particles break easily. Let's take a look at hydrophobic or water hating. Some siliceous aggregates such as quartz are hydrophobic or water liking, meaning that they have a greater affinity for water than for asphalt due to their surface charges. This may lead to stripping as asphalt coatings comes away from the particles in the presence of water. Free from deleterious substances, again clay particles, dust, dirt, and lightweight pieces may lead to a lower quality asphalt film on the aggregate particles or may also result in breaking of some of these particles or breaking away of some. And we've already discussed the requirements or the measurements of these properties we discussed earlier in some of the other module lectures. But we're looking at the measure of susceptibility to stripping. It's ASTM D1075. With this test, samples are immersed in water for a specific time period, and the resulting loss in strength is compared with the control samples to indicate resistance to stripping. Typical specifications for the aggregates for dense graded asphalt concrete can be found in the following tables. And again, we're going to see those in the PowerPoint presentations and also as attachments in the announcements that will be posted. So keep in mind that some authorities require the use of 100% crushed rock and a high portion of manufactured sand that is obtained from crushing operations for high volume pavement surfaces. Our super pave requirements for aggregate. Super pave requirements for aggregate include limits of gradation, angularity of both the coarse and fine aggregates, amount of thin or elongated particles in the coarse, and the clay content of the fine aggregate that we have. Other properties and the designated source properties depend on the local source, and experienced individuals have to or go into the selection process and are left to the local agencies to specify what they can use. These properties include the toughness or abrasion resistance, soundness, and deleterious material content. Gradation requirements include control points for minimum and maximum percentages, passing certain sieve sizes, but also a restricted zone as shown in the following figure. And again, you're going to see that in the PowerPoint presentation. Super pave gradation limits. This restricted zone limits the amount of medium to fine sand with their rounded grains that can be utilized within the asphalt mix content. These medium and fine sands can be detrimental to the mix and may make it difficult to reach the minimum VMA values that are required. In order to meet these standards, a significant amount of manufactured or processed materials, such as screen materials from the crushed rock, must be added to the fine aggregate to the minimum specification requirements. Of course, in the Module 4, we looked at the grain distribution curves, and we would repeat these same procedures based on the 0.45 power graphs. The maximum density line is shown for guidance when blending aggregates for a dense gradation, except in the area of the restricted zone. Of course, this makes sense because it is the restricted zone. Aggregate angularity. Angularity of both the coarse and the fine aggregate must be measured to ensure compliance with the mix specifications. Coarse aggregate, of course, gravel sources. A sample of the particles is examined and divided into 3 stacks. One stack contains particles without any fractured faces. The second stack contains particles with 1 fractured face. And of course, the third stack contains particles that have 2 or more fractured faces. The percent or the particle with 1 fractured face and with 2 or more is determined and compared with the requirements in the following table. Again, you'll look at the PowerPoint presentation for that table. Our fine aggregate angularity is measured by pouring a dry sample into a cylinder of a known volume. The mass of the sand is in the cylinder is measured. The mass of the sand that the cylinder would hold, if there were no air voids, can be calculated from the bulk density or relative density or the specific gravity of the sand. And from this point, we can calculate or determine the percent of air voids in the sand. There's some examples that are in the PowerPoint presentation that will help you. So you take a look at them and then you'll see how we can go about determining these relative densities or the bulk relative density or the specific gravity. The coarse aggregate, the amount of thin or elongated particles in a sample of coarse aggregate from the gravel source is measured by examining a sample of the aggregate. The length of each particle is measured by its width or thickness, and the least measured value is utilized. If the length is over 5 times the magnitude of the second measurement, it is considered to be a flat or elongated particle. These particles must break when being mixed, or these particles may break, I should say, when being mixed into an asphalt concrete or within the overall paving process or operation, leaving particles that are not properly coated within the overall binder material. Super pave requirements indicate that the percent of flat or, again, elongated particles shall not exceed 10% of any pavement with an ESAL of over 1 million. Our asphalt concrete mix design. The design of an asphalt concrete mixture includes the selection of the best blend of aggregates that will meet the design specifications for the optimum asphalt content that is also economically cost effective based on the environmental elements it must withstand. So we look at one here. A standard mix design includes the following steps. We get the selection of the aggregate proportions to meet the specifications. We conduct trial mixes at a range of asphalt contents and measuring the resulting physical properties of the sample. Analyzing the results to obtain the optimum asphalt content and to determine if the specifications can be met. Of course, we're going to repeat with additional trial mixes using different aggregate blends until a suitable design is found for the specific environmental area that we're going to place this asphalt surface in. The 2 most common methods for making and evaluating trial mixes are the following. It's the Marshall method, which we looked at, and of course the high beam method. The super pave method developed by the Strategic Highway Research Program is becoming the standard method. This concludes the Module 7 lecture on asphalt pavements and materials. And again, please make sure that you view the PowerPoint presentations. There's examples in there that will help you with the course assignments that you will need to take a look at.